A very good day to the spectators. I am Janit Kaur and this is my Ell Project submission titled DC Motor. In this presentation, the following discussion points would be construction of a DC motor, its working, mathematical angle and back EMF, and the applications of a DC motor. Starting off with the construction of a DC motor. It consists of the following mentioned components. Number 1. Yoke. It is the magnetic core of stator. It provides path for the pole flux phi and carries half of it. It carries stationary flux and hence there is no eddy current. Field poles. They consist of pole core and pole shoe. They produce the magnetic flux when the field winding is excited. Field winding. These are the insulated current carrying coils on a field magnet that create a rotating magnetic field inside the motor. Interpoles. This winding is connected in series with the armature winding. It is used to overcome the effects of armature reactance and self-induction in the machine. Continuing with the construction of DC motor, we have armature core. It is the rotor of a DC machine. It houses the armature conductor in its slot and provides low reluctance path to the magnetic flux. Pole shoe. It enlarges the area of armature core to come across the flux, which is necessary to produce larger induced EMF. Armature winding. It is attached to the rotor and conducts AC on DC machines due to the commutator action, periodically reversing current direction. Along with it, I have also attached a pic of the DC motor with its components. We have the field pole, the field winding, the spider, the laminated armature core, the pole shoe, the yoke or frame, the shaft, bearing, interpole winding, base, riser, and end cover. Now, coming to the stepwise working of a DC motor. The first step is, the motor is powered by DC current, which creates a magnetic field affecting the magnets on the rotor. Step 2, the first step causes the rotor to start rotating. Step 3, the commutator ensures that the rotor keeps rotating. Now, how does the commutator ensure that? So the reason is, the commutator reverses magnetic field when rotor is aligned to it. Otherwise, the rotor would stop rotating. As can be seen in the diagram, all the 4 steps have been well explained along with the processes. Moving on to the mathematical angle, the working principles of DC motor are: number 1, in the presence of electrical and magnetic field, the current carrying conductor experiences torque and develops a tendency to move. Number 2, given by Lenz's law, EMF generated in a time-varying flux opposes the cause of change of flux, that is, E is minus d phi by dt. Average voltage induced in one coil in one turn is 2p into n into phi, where p is number of poles, n is rounds per second, and phi is flux. Average EMF per conductor is p into n into phi. EMF across brush is given by Zp by A into n into phi, where Z is the total number of conductors and A is the number of parallel paths between brushes. Substituting n by omega, we get 60 into Zp by 2 pi A into omega into phi, where omega is 2 pi n by 60. Moving on to the second last part, which is the back EMF. Back EMF is also characterized by EMF across a brush. As we saw in the previous slide, the EMF across brush is given by Zp by 2 pi A into omega into phi. Now let Zp by 2 pi A be Kb, where Kb is a constant. So we get that EMF across brush is Kb into omega into phi. Torque developed is Kb into Ia into phi. Along with it, I have also attached a graph of voltage versus time. Moving on to the last part of the presentation, which is applications of DC motor. It is used in portable applications using battery power. Shunt DC motor is used in blowers and fans. Series DC motor in cranes, elevators, etc. and cumulative compound DC motor in rolling mills. A very warm thank you for watching the presentation. Hope you liked it.